You're here because you want to master the gaseous state with a University of Cambridge graduate. Let's begin. You can start by going down in the link below to download a copy of the notes so that you can sit through the lecture with me as I go through the gaseous state. In the gaseous state, we will be covering what is ideal gas behavior, what are the deviations from it, this equation called PV equals nRT, and how do we calculate the partial pressures of gases. As usual, before we start, do remember that there's a list of learning outcomes for every chapter, and we will be referencing to it as we go along the lecture. So if there's one thing to take away from the gaseous state, it is this equation PV equals nRT. So P stands for pressure, V stands for volume, N stands for mole, R is a constant, which is usually 8.314, and T is temperature. In this equation, you always have to take note about the units that are being used for your values when you're inputting into your equation, because they follow a strict set of values. So in this equation, you always have to convert the units into, for pressure it will be Pascal, for volume it will be meter cube, for N it will be moles, for R it's always the same, it will just be 8.314, and for temperature, always make sure that it's in Kelvin. Now, how do I convert my typical units into these units that we see over here? For pressure, we usually get units like bar, and 1 bar equals to 10,000 pascals, or we get ATM, which actually stands for atmospheric pressure, and 1 ATM equals to 101,325 pascals. For volume wise, we tend to see dm cube, and 1000 dm cube equals to a single meter cube. Next up is cm cube, and actually 1 million cm cube equals to 1 meter cube. So these are some typical ways you can convert for pressure and volume. For N, we usually just use moles, and for T, always remember that you could get degrees Celsius, and whatever degrees Celsius you have, let's say you have 8 degrees Celsius, you just have to plus 273, and you will get the equivalent for Kelvin. So why is this equation so important? It's because just by knowing this equation alone, you can already determine several relationships between pressure, volume, and temperature, and number of moles, plus any other ways you can manipulate these units. So here's an example. From the equation, you can determine several conclusions, like you can see that volume is actually directly proportional to 1 over P, or you could say it's inversely proportional to pressure. And how I know that is actually because PV equals to nRT, and this is equivalent to P equals to nRT times 1 over V. So because of that, there's already an inverse relationship, right? And at constant temperature, your PV equals to nRT. nRT would be a constant, right? So that means the pressure and volume are just proportional to each other. And if I ever change my pressure, or if I ever change my volume, it would affect the other one directly. So P1V1 would equal to P2V2. Of course, given that temperature is a constant. So here are some of the relationships that they like to test in MCQ especially. So when you're given a graph, I want you to just apply the concept of using the equation and not just simply memorize these graphs. So when I see a graph over here, V is the y-axis and P is the x-axis, I just want to put them accordingly. So if V is the y-axis, I will leave V on the left side and manipulate it. And because I see this is an inversely proportional relationship, then obviously the relationship would just be a curve like this, right? Now, if the graph, it was a PV against V graph, we know that PV equals to nRT. So by using the equation PV equals nRT, and I leave PV on the left side, And I see that there's no V on the right side. So that means that there's actually no relationship between PV and V. So the graph would just be a straight line. And next, for V against 1 over P, we already know that V is directly proportional to 1 over P by using the equation. So this is just a straight line. Now, wasn't that so simple? And now, what about the relationship between volume and temperature? Same thing. If we were to put PV equals to nRT, I would already see that V is directly proportional to T because V is on the left side. And if I were to shift things around over here, this is the relationship. Now, at constant pressure, you would see that this is a constant. And with that being a constant, this means that V1 over T1 will equal to V2 over T2. This is because you can draw a rough parallel over here and see that V over T equals to NR over P. And if this is a constant, when pressure is constant, means V would be proportional to T, and any effect on V will have an effect on T, and vice versa as well. So again, when I have a graph like this, I always have to analyze it using the equation. So with a V against T graph, we already know that the relationship is a directly proportional one using the equation. Now it's about seeing how I can fit the equation into the graph. So with V on the y-axis and T on the x-axis, and T is especially in Kelvin, right? We know that T, the lowest T can ever go is 0. So from a 0, we can already plot the graph as shown. Now what happens if T is in degrees Celsius? When T is in degrees Celsius, it can go to as low as minus 273. Okay? And because of that, we have negative degrees Celsius in play. We always have to take into account the negatives. So with that being said, your graph would already start from about here, which is as long as it's in the negative axis for the x-axis, then we're fine. And it's still the same relationship. So it will still be directly proportional and an increase accordingly. Now what about if we have constant temperature and pressure? Then using the formula PV equals to nRT, right, we can shift it accordingly and see that V is also directly proportional to moles. So if I shift it like this, I can see that this is actually a constant. And this gives rise to the equation where V1N1 equals to V2N2. So when I change the number of moles of a gas, this should directly affect the volume. And this graph, if I were to interpret it correctly, so if V is directly proportional to N, looking at the sides of the equation, this would mean that there is a straight line up. Now we move on to partial pressure. Partial pressure is a very tricky subject and it gets many students really confused. And that's why I'm here to break it down for you. Partial pressure is defined as like the molar fraction of gases in the overall system to determine each of their partial pressures. And what I mean by that is, if you take the partial pressure of gas A, for example, and add it to the partial pressure of gas B, and so on and so forth until you cover all the gases, you should be able to get the total pressure of the gases in the whole system. So if I were to break down the pressure total into their respective partial pressures, I can further break down the partial pressures into their own nRT over V as shown over here, right? And the only thing that's different is actually the N, because the R, T, and V would be the same for both the gases because they are in the same system. You can also take note because V is the volume of the container. Now, since the only difference is the N, which is the mole of that particular gas, you can summarize the equation into the final one over here. And realize that partial pressure is really just determined by the moles of each gas within the system. So if we come over here, the conclusion is that partial pressure is determined by the molar fraction. So if I have, let's say, 10 moles of gas in a room, and 1 mole of gas is occupied by my fart, for example, the partial pressure of my fart in the whole system would be 1 over 10 times the whole pressure. The assumption of ideal gases is important because we should know that there really isn't such thing as an ideal gas. It's kind of a theoretical and made up belief. These are the rules of what determines an ideal gas is ideal. So we have to memorize each of these because they are very likely to get tested. So number one, the volume of each particle is negligible. So volume is negligible compared to the total volume. Number two, negligible forces of attraction between my particles. Number three, there's perfectly elastic collision. So whenever they collide with each other or they collide with the container or the walls of the system, there is actually no loss in kinetic energy. And four, the particles are always in constant and random motion. So please memorize these. And it's so important because you can apply this to the answering techniques in the following few parts. And also, the average Ke of my particles is proportional to temperature. So what are some of the behaviors of ideal gases? In high pressure, there's actually a smaller volume. And when we have higher pressure, the attractive forces actually become more significant. You can think of it like the particles are being forced to be closer to one another, and therefore your usual intermolecular forces will come into play more significantly. And second, when you increase pressure, the volume would decrease. And because of that, the volume of each gas particle is going to be more significant relative to the total volume of your gas. Remember that gas particles don't really have negligible volume. The molecule itself does take up space. So whenever I have a graph of PV against P, the relationship between PV against P for a real gas would deviate from an ideal gas. And that is because you can see that there's an initial dip at first followed by an increase. So if I break it into two parts, the initial dip is because of the intermolecular forces not really becoming negligible as you increase pressure. Again, this is because you force the gas particles to be closer and the attractive forces between the particles become more significant. So taking that into consideration, when your attractive forces are more significant, your pressure would be lower than expected because pressure is about the molecules hitting the walls, and the molecules cannot exert enough force or the same amount of force on the walls if there is something pulling it back, which is the attractive forces. Then there is this increase over here, and this is because as you increase pressure even more, the volume of your particles are more significant. So because of that, your V would be much higher, and therefore your real gas PV would be higher than the ideal gas. At lower temperatures, your gas molecules actually behave more ideally. So let me explain. When you have lower temperature, your volume would decrease because now the gas particles volumes are now more significant compared to the total volume of the gas. And at lower temperatures, this is more important, your Ke of your gas particles will decrease. So because of that, the particles move slower, they travel slower, they collide less, and therefore your intermolecular forces would definitely be more significant. And because of that, your PV is actually smaller than it should be. So when you look at the graph, you'll see that a higher temperature means it deviates more. But at a lower temperature, it deviates less. Now what about if you have strong intermolecular forces between your gas particles compared to weaker intermolecular forces? So a typical example is NH3, ammonia, against helium. When you have stronger intermolecular forces like hydrogen bonds, for example, this already means that your intermolecular forces are less negligible, and therefore your gas would behave less ideally and deviate more. So if you see NH3, there is very clearly a more significant deviation compared to helium because helium has weak ID between the helium atoms, And because they are very weak, you can consider them pretty much negligible. Of course, they're not negligible, but they definitely are more negligible than hydrogen bonds, and therefore your helium atoms will appear more ideally than the NH3 atoms. So that's all for gaseous state, a really short topic that utilizes PV equals nRT a lot and needs you to understand the assumptions of ideal gases. If you like this kind of content, be sure to hit the subscribe button so that you can get more frequent updates from this channel. And if you want to enroll in my online classes, be sure to click the link below so that you can book a free call with me and I can run through your past exam papers and perhaps go through your challenges and difficulties and work on the next way forward. I'll see you in the next video.